So, at the beginning of the ride, the coaster is at the bottom of the hill and not moving. So, would it have any kinetic energy? If it's not moving, no kinetic energy. Now, of course, all things have some temperature, so down at the tiny atomic itty-bitty, like teeny tiny level, it probably does have a little kinetic energy in that regard, but that's the microscopic, and I'm asking you more about the macroscopic. No kinetic energy, macroscopic, like big picture, okay? All right, then gravitational potential energy. Is it above the ground? Does it have some height? Well, this says that it is 5 meters off the ground, so yes, it would have some height. Okay. All right, mechanical energy. Well, today when you guys did your vocab term, you should have learned that mechanical energy has a few different types. One of them is kinetic energy. Another one is gravitational potential energy. So since we do have some gravitational potential energy, yes, we should have some. How about non-mechanical energy? Well, like I was saying, it probably has some amount of temperature. So yeah, it probably has some thermal energy, which means it would have some non-mechanical energy. The only thing that it doesn't have right now, because it is not moving, is the kinetic energy. Now, let's actually talk about calculating the amount of energy that the car has before it ever starts moving. So we're going to show some work down here, and I'm going to do this as an example calculation. So we haven't learned the calculations for different types of energy yet, so I'm going to go ahead right here and teach you the calculation for gravitational potential energy. So the unit that we're going to, or the way that we're going to describe it is there's actually this letter U. Well, actually, let's go ahead and use a PE. We'll use PE for potential energy. And then I like to put a little subscript G next to it, kind of like when we would do FG for our force due to gravity. This is potential energy due to gravity, technically, gravitational potential energy, so putting that little G there kind of makes sense. Here's the formula. The formula is M, which stands for mass, times G, which stands for gravity. Okay. And then times H, which stands for height. So let me write that a little bit shorter. PEG is equal to MGH. Remember, when we put the letters right next to each other, that means multiply. So now all we have to do is plug in the information that we know. We need the mass. I told you the mass actually up here in this picture. It's 1230 kilograms. I picked that because it was kind of a reasonable amount, and also because it says 1, 2, 3, and then a 0. So it's easy to remember, hopefully. All right, so that is going to be 1,230 kilograms times, well, what is G? G is the same thing that we've been using. We're still talking about how things are happening on Earth, so we want to use 9.8 meters per second squared. And then we're going to do times our height, and the height at this position is 5 meters off the ground. So we multiply by 5 meters. All right, so now we just need to do a little math. And I didn't have my calculator sitting with me, so I am going to use my very fancy cellular device. Okay, so let's go ahead and do 1230 times 9.8. And notice the squared is part of the unit. The seconds are what is squared. We don't have to square this number. When I was grading tests, I noticed that a lot of people were squaring the 9.8. You don't need to do that. So just 1230 times 9.8 times 5. And that gets us our answer, which is a pretty big number, but it should be, because we're talking about how much potential energy a whole roller coaster car full of people is. So that is going to be 60,270. And do you guys remember what the unit for energy is? Joules. So we can just write a capital J for joules. You don't have to write it all out. And there we go. So let's go ahead and write that final answer in the blank. 60270 J joules. So that's how many joules of energy that car has before it ever starts rolling, before it goes up to the top of that hill. All right, now I'm actually going to help you guys work on the next page, so go ahead and turn the page. I've got mine printed on another page. And we're going to work through some of these problems together, okay? All right, so we have a chain on the track connected to a motor, pulls the car up to the top of the first hill, which is a height of 45 meters high. Please notice that this is 40 meters higher than where it started. So this motor has not lifted the cart 45 meters, it's only lifted it 40 because it started at 5 already. How much energy does the car have at the top of the hill? Assume that it comes to a stop at the top of the hill because we don't want to have any kinetic energy, so it's going to make things a little easier. So again, we're going to show our work down here, and then we'll write our answer in this blank space. Okay, so again, since the only kind of energy that it's going to have here is that gravitational potential energy, then we're going to use PEG is equal to m times g times h. So that is equal to, the mass is the same that it was before, 1230 kilograms, times gravity, the same as always, 9.8 meters per second squared, times the height. This new height is now 45 meters high. Okay, there we go. So let's multiply these numbers together. I'm just going to be real fancy here and backspace 45. And now I have 542,430 joules. There we are. Let's go ahead and plug in this number right here, 542,430 joules as our final answer. All right, so before we started going up that hill, we had 60,270 joules, and now we have, 542,430 joules. Well, we went up 40 meters, so that's a lot. Okay, so now, number 4 asks us to calculate the change in our energy. Well, that change just means how much that we ended with minus how much we started with. Okay? Anytime we're dealing with a change in energy, when we deal with that delta, so this is delta E, we're just thinking about what things ended with, subtract what we started with. So our change in energy, delta E, is going to be equal to our ending energy minus our starting energy. In this situation, our ending energy was 542,430 joules minus our starting energy was, there we go, 60,270 joules. Easy enough. So now I'm going to go ahead and do this number minus 60270, and that's going to give me 482,160 joules. Let's go ahead and write that into our final answer, 82160 joules. So that's how much the energy changed, how much it increased. If we got a negative number, then we would have had a decrease in energy. Okay, so if the height at position 1 is 45 meters, how much work does the motor on the track need to do to lift the car to that height? And then your hint is that weight is Fg, and that Fg is equal to mg, which is mass times gravity, and that's 9.8. Okay, so we need to calculate work. So think back to that formula for work. Remember, work is equal to force times distance. And just like in the examples that we've done when we were lifting the mass in class, and then when we ran up the stairs, the force that we were applying was the weight that we were lifting up. And that's going to be the same thing here. The problem is, I did not give you the weight of that car. I gave you the mass in kilograms. But we know how to figure out what that weight is. We just need to multiply the mass times 9.8, right? So what we are going to actually do here is not just Fg, or excuse me, force times d, we're going to do mass times gravity first. So we're going to do, instead of F, we're going to write m times g, and then we're going to multiply that times the distance that we're lifting. Okay? So that is going to be, my mass is 1230 kilograms times 9.8 meters per second squared. And then we're going to multiply that times the distance that we actually lifted. So remember, we looked at where we were at 5 meters high and where we were at 45 meters high. Now we're talking about just that change. The actual distance that we lifted was only 40 meters. So we're going to multiply that times 40 meters. That is equal to, let's see, clear. Oop, let me just do that and then clear. Okay, so now 1230 times 9.8 is equal to that, times 40 is equal to that. All right, and we get 482,160 joules. That is how much work we did, 482,160 joules. Hey, doesn't that number look familiar? Boom! Yes, it does! Remember when you wrote down your word of the day and I told you that delta E is equal to work? It is in fact equal to work. Boom! We just brought things together. Isn't that amazing? All right. So I want to make sure everybody has a chance to get caught up on this. So take a second, work on that, and then I want you guys to go ahead and answer question 6. How does work relate to change in energy? And then I think you guys can even write your answer to question 7. This is actually calculating power. Remember, power is equal to work divided by time. Using that information, will you guys please go ahead and answer 6 and 7 for me? All right, I'll see you in a couple minutes.